Second would be, say, if you have a simply supported beam, which is like the most basic one, wherein you have one end which is pin support and the other is kind of a roller support, right? So this is a very basic single span beam condition. And like the thing is, this is wherein whatever load you apply, there's no moment reactions developed on either side. It's just the translation ones. So whatever loads you apply, based on that, the reaction is actually produced in these beams at the corresponding joints. So if you apply a vertical load, you will see that vertical reaction is developed on this joint as well as this joint. But if you apply, say, an axial load, in that case, as we know, like, since this can easily glide over, so there's no horizontal reaction developed here. So the entire axial load that you apply in this beam would actually be taken by this support here, because this support is actually capable of making sure that there's no translation along that degree of freedom. Good example of this kind of beam would be, say, if you consider a composite beam structure, right, wherein most of the beams are actually considered as simply supported to get the composite action, which is not really in the scope of this seminar, but then just wanted to let you know like what are the different real life examples of these kind of boundary conditions. The third one would be, say, a beam which is kind of running over supports. So that running over of the support is basically known as an overhang. So this one is, say, an overhang, this one here is an overhang, and this could be on one side as well or both sides of the structure as well. And then this kind of happens when, say, you have a beam and then you have a column here. So this support is basically a column, but then the column can't really go all the way to the face of the building. So in that case, you have to stop short the column right before the face of the building. But then since you have flooring over here which is supported, so this beam actually has to extend over so that it can pick up the floor edge over there and the facade and things like that, which is going to be existing over here. So that's one good example of where you would actually come up with these kind of beams. And then even at roof, wherein when you have a column in the intermediate location, but then you need to pick up the facade which is kind of hanging off of the roof. So in that case, you'll have to come up with this kind of a beam. That's one example. And then there's this example wherein it's a propped condition or a propped cantilever where one end is fixed. So that means this end is actually able to pick up all of the translational degree of freedom reactions. But then over here, it's just a roller support. So one good example of this would be, say, if you have a concrete beam which is, say, supported off of a wall about its minor axis. So say if it's a shear wall, but then this wall is, or this beam is kind of supported off of the minor axis of the walls. So we typically don't design these walls for any minor axis moment. So in that case, that joint here does not really have much rotational fixity, so it's more like a pinned support here, or a roller support rather, for that matter. But then over here, if you have a pretty stiff column and then you have this beam framing into that column, in that case you can definitely develop that fixity over there. So that's one example of fixed support and the roller support. So this is known as a propped cantilever beam. And then say this beam here, for example, say it's a single span beam. So this is a good example of what I was talking about when we said that splicing condition, right? So if it was a pinned beam in that case, and then you provide internal hinge where to say, so if, for example, if it was a simply supported beam and then that was, say, pretty long and you can't really ship that, so you end up providing a splice connection here. So if it's a shear splice, that means there's no moment that's going to be transferred. And if this was a pin support and this was a roller support, in that case, obviously this structure will become unstable, right? So in that case, to avoid that, what we are doing here is, like, say you introduce a shear type internal hinge here, and then you have a fixed end here, so that this becomes a stable structure now. So this is one good example wherein you have a beam which is spliced with a shear connection. In that case, you can actually have this kind of boundary condition here as well, where you have a fixity on one support, say it's a column, and then you have a shear splice connection here, and then you have this another connection to another girder or a column, which is like a pinned condition. So basically, it's up to us, like, what kind of support conditions we want to have the structure so that it's kind of stable. So, like, as of now, we have just looked at some of the single span conditions. We can actually take a look at some multiple span conditions as well, which is actually very common in RCC structures. I mean, for example, it could be more than a single span, say it's a two span or maybe three span or five span beam, which is continuous over the support. So, I mean, whenever we load any structure, there's going to be these additional supports that we have, and therefore they will develop their own reactions, and then there'll be, because of the continuity over the beam, or over the support rather, there'll be a development of kind of a negative moment for gravity loads and all. So this is actually a very common thing in the residential projects as well, wherein you have multiple span beams, or it could be, say, a parking structure as well, where you have multiple span post tension structures as well. So wanted to touch upon, I mean, so we actually have these different boundary conditions which we can ensure while we are designing and detailing the connections. So this was it in terms of, just coming up with different types of beams that we work with in our field. And then now this is something which is very basic again. So say when you have a beam which is I've shown in red, and then if and that is a neutral axis, right? And I guess most of us would be aware of what a neutral axis is, right? That's the line along depth wherein where there's no deformation in the or there's no strain at all in the beam. So the thing is, whenever a beam is kind of loaded, it obviously has to bend, and therefore whatever load is applied, so there's some work done by the load, and then that is actually stored in the structure as strain energy is what we call. So what I'm trying to show here is like when you apply a load, the beam actually deflects, and the deflected shape is say shown in green here. So the vertical displacement that we typically deal with y is actually the vertical displacement of the neutral axis, for example. And then if now the thing is we have these different or different beam equations that we have, which is kind of the basic of any beam analysis, right? So if you have a beam which is subjected to a uniform load, or maybe not a uniform load, but say it's a load which is a function of the space. So say that load is wx. So we have these different conditions here, which says the force differential of the vertical deflection curve with respect to the space, that's actually equal to the loading intensity of on this beam over ei, where e is the modulus of velocity of the beam and I is the moment of inertia. So that's a very basic one. And then if you integrate it once with respect to x, you get the third differential of the vertical displacement over x, and that basically gives us nothing but the shear force variation or shear force at a given section in a beam. And then if you integrate it further, so you reach the second derivative of y, which is d2y by dx2, which is also known as the curvature of the beam, and that's actually equal to the bending moment over ei. And then lastly, dy dx, which is actually the slope of the beam at any given section. So that is actually theta. So these are the few equations which kind of govern or the differential equations which kind of govern the behavior or response of a beam. And then based on this, and then also, like, since we have a differential equation to solve this beam, we also need to have a set of boundary conditions, right, to solve this differential equation. And that's where the support conditions actually come into picture, because that's where it kind of gives us, okay, so for example, say if you have a pinned support or a roller support, in that case, as I said, like at the supports, since you don't have any rotational degree of freedom logged, in that case the moment over there would be kind of zero. So that's the reason the second derivative of the deflection with respect to x would be zero. Say the vertical deflection at that point is also zero, right? Because that's a support, that's a vertical translation logged kind of a support. So over there, y would be zero, which is your vertical displacement. And then we have this equation here, which is also very important, and that's going to come in very handy when you're reviewing the bending moment and shear force diagram, which is that the slope of the bending moment diagram actually gives the shear force, and that's what we saw in the previous slide as well, right? Because the third derivative was actually the shear force, and the second derivative was the bending moment. So this is also a very important equation that we kind of try and come up with when we deal with the different bending moment and shear force diagrams. So these are some of the very basic equations that we typically need to be aware of for any structure. I mean, even though we are saying it's for beam, but this actually applies to even columns as well, where if a column is seeing any flexure, in that case, these apply to the columns as well.